So this is my demonstration. I just want to apologize for the lack of technology. I had a tough time trying to figure out how to screen share and also show my face. So hopefully this more realistic interface works. The first problem is talking about U substitution, explain what it is. So before, when we were taking derivatives and we didn't have an integral, we would use the chain rule. But since we're using an integral, we use U substitution. So what I always do is I try and make U as the inside function. In this case, it would be the x squared. So I make U as the x squared, and I do some algebra and find du to be 2x dx, and then I find dx to be du over 2x. And so since I'm now working in u instead of x, I just substitute that in. So now I have 10x of sine of u equals du over 2x. And so something that always tells me that I'm going along the right track is when my dx, when I replace it with the new function, in this case du over 2x, is going to lead to something canceling. For me, when that is not the case, it's kind of a sign that something is not gone right. So in this case, the 2x is going to cancel out with the 10x, leaving a 5 we can pull through. And now it's just the integral of sine u du. Of course, we know that as we know the derivative of sine to be negative cosine, and then we just resubstitute in the u, which was x squared, giving us a final answer of negative 5 cosine of x squared plus c. So number 2 is the functions of 10x sine of x cubed dx and 10x sine of x dx, and explain why U substitution would not work in this case. In the previous example, I explained how, for me at least, a key kind of sign that I'm on the right track is when the U sub leads to something canceling. In both of these, this would not be the case. So in this one, we get, if we would make the U the inside function, would be x cubed, and the derivative of that would be du equals 3x squared dx. And then to isolate dx so that we can resubstitute it back in, we would get du is equal to 3x squared. And that would end up leaving us with an x in the denominator, which we don't want. We want it clean across the board. So that's why that one would not work. And kind of conversely, in this next one of 10x sine of x, we would make x the u, and we would get du equals dx after some algebra. And that again would leave us with an x, not this time in the denominator, but in the numerator this time, which is still a problem, which is why in this case, the U substitution would not work, because it wouldn't allow us to simplify the equation further. So number 3 is talking about integration by parts. So in the past, we would use the product rule, which is first derivative of second plus second derivative of the first. But when we're working with integrals, we don't use the product rule. We use the equation uv minus the integral of v du. So in this case, something that, a little trick that I learned that helped me would, when looking to choose what u would be, is look for logarithm, then inverse, then algebra. And normally, at least for me, so in this one, I find, it's not a log, not an inverse, but we do find an algebra in the form of 10x. So I make u as 10x, and then I get du as 10 dx, with dx being 10 du to use later. So if 10x is u, then dv would have to be, so the equation is u dv equals uv minus the integral v du. So if 10x is u, then dv would have to be sine of x dx. And doing some reverse integration, we would get v is equal to negative cosine of x. So to rewrite it, we would get 10x, so u 10x times v, negative cosine x, minus the integral v, negative cosine x, times du, which is 10 dx. So just multiplying out, I get negative 10x cosine of x plus 10, as we pull that through the integral, cosine of x dx. And then to finish it up, we get negative 10x cosine of x plus 10 sine of x as we take the derivative plus the constant of differentiation. So number 4 talks about how choosing the wrong u and the wrong dv would complicate things. We're still using the equation of u dv equals uv minus the integral v du. So as I mentioned earlier, I always look for logarithm, inverse, or algebra as my first 3. So in this case, the correct u to use would be x squared. So the wrong u would be e to the x, meaning that du for that incorrect u would be e to the x dx, making dv x squared dx. And that, working backwards, that would make u x cubed over 3. So if we brought that down into the formula uv minus the integral v du, that would give us e to the x equal e to the x times x cubed over 3 minus the integral x cubed over 3 times e to the x dx. And something that I learned is that if the powers are increasing, that means that we're expanding the equation, not simplifying it, which means that we're going in the wrong direction. So in this case, choosing the wrong u and the wrong dv would only complicate the equation. It would elongate it instead of simplifying it. So that means that we've chosen the wrong u and the wrong dv. And if we were trying to solve, it would be time to reevaluate our selections. So problem number 5 deals with trig substitution. And so one of the things that I think trig substitution helps us do, it gives us a visual way to look at the problem, which I think is really helpful for me at least. And number 2, it gives us an opportunity through sometimes drawing out right triangles to convert to trig so that we can use identities. So in this case, when we're looking at the integral of x squared plus 16, thinking ahead, we can kind of use a right triangle and look at the angle theta, which is what we're looking for, and kind of label the different sides of the integral, like the square root of 16, obviously looking ahead would be 4, and x right here. And so if we were to use Pythagorean theorem, we would get for the hypotenuse side, or this side of the triangle, the square root of x squared plus 16. And we could use that identity to use x equals a tan theta. So then bringing it back into the integral, the integral of the square root of 4 tan theta plus, and that quantity squared plus 16 is equal to 16 tan theta squared plus 16, which is equal to 16 tan theta squared plus 1, which when we take out of the integral is equal to 4 secant squared, 4 secant squared. So we get 4 secant theta times 4 secant squared theta d theta. Flipping the page. So we end up getting a 16, pulling that through the integral, secant cubed of theta d theta. And so integrating by parts, we end up getting 8 secant theta tan theta plus 8 of the natural log of secant theta plus tan theta plus the constant of differentiation. So after simplifying and clearing some of that up, we get 8 times the quantity x squared, the square root of x squared plus 16 over 4 times x over 4, coming back to our triangle. Obviously using the different trig identities and our values to get these values. So we have that first term plus 8 ln times the quantity of x squared plus 16 over 4 plus x over 4. So to clean it up fully, we get x times the square root of x squared plus 16 over 2, that whole quantity over 2, plus 8 ln times the square root of x squared plus 16 plus x, not under the square root, over 4, plus the constant of differentiation. So just to kind of sum it up, trig identities, by using a right triangle, we can kind of get a visual of how to look at the problem and kind of get it to a stage where we can use our trig identities to substitute in terms and get it so that we can simplify it and solve the problem. So the last part of the demonstration asks us to summarize one of the sections of the notes. And so I'm going to talk about the volume. And so we can kind of determine like what a solid, we can put a solid on a graph by putting like a region R on the XY plane and putting a line that we can rotate this region around in order to kind of create something that we can kind of visually grasp as something we can take the volume of. So by rotating around this line, we can create a visual that can help us to understand these equations right here. So volume equals the integral from a to b of pi of f of x squared dx. By furthering this equation, we can kind of we can get a grasp, we can solve for what the volume is of this region right here, which was originally this, after we then flipped it around this line. And this is called the washer method, to try and visualize like what a washer is, to kind of get a sense of like this circle right here, this is what we're looking for. Get a sense of what the volume of this is, like what, if this was a cup, so to speak, this area right here, how much water would it take to fill up that cup? So that's what this concept and this equation allows us to do.